Well, hello students. Free fall, vertical acceleration, finally. So we've looked at constant velocity, we've looked at horizontal acceleration, and we've looked at problems that have both constant velocity and constant acceleration, horizontal components to them. So we're going to finally move to vertical, looking in the y direction, up and down, and objects in free fall. So for this particular object here, there's a point particle diagram, or what we'd like to also call a motion diagram. And the description is this object has been released from rest. It could be somebody at a windowsill holding a flower pot, and they just decide to, whoops, drop it. So starting from rest, the velocity is 0, and then each equal increment of time, the velocity is speeding up for this flower pot. And so with this motion diagram, since the velocity vectors are increasing in a negative direction, that's letting you know that the acceleration vector should be included over here, showing that acceleration is in the negative direction. So when we look at this, this is our motion diagram. Let's move over here to a graph. So here's our graph, and it's a velocity time graph, as you can tell. And if you notice here, we have a subscript on velocity with a y. So that's letting us know here we're looking at the y velocity only. And this particular example has no horizontal component. This is only a vertical component because the object has been dropped, so it's only heading down. For this chapter, we're only looking at the velocity in the y direction, and acceleration only in the y direction. So it's only going to be one-dimensional motion. That's why chapter 2 is called one-dimensional motion. So we won't have both x and y not until we get to chapter 3 when we look at projectile motion. So anyways, let's look at the origin here. So it probably doesn't surprise you that the velocity is 0 at the beginning of this event, this physical event, because it was dropped from rest. So there's your 0. So since we know that the acceleration due to gravity here on Earth is negative 9.8 meters per second squared. I've also said you could use negative 10 meters per second squared. On the AP test, you will use negative 10 meters per second squared. Problems that you do in the college physics book, if I assign you problems, you'll use the negative 9.8 meters per second squared because the answers in the back of the book correspond with this particular given piece of information. So let's take a look at this graph. So at the instant it's let go, right then at that very moment it is 0. So you let it go and now it begins to speed up towards the ground. So in the first second, after 1 second has elapsed, it's a negative 9.8 meters per second. That's the velocity. After the second has elapsed, now the velocity is negative 19.6 meters per second. And then after the third second has elapsed, now this flower pot is heading down at negative 29.4 meters per second. So this flower pot is heading down and speeding up in the negative direction. So whenever you look at a slope of a line on a VT graph, it gives you acceleration. So I want you to notice two things about this line. First off, it's heading down to the right, so that means it's negative. And the second piece of information, it's not a curve. So whether our velocity is constant, y'all remember seeing that whenever it was flat and horizontal, this is also a straight line. It's not a curve. So in this course, in this AP Physics course, you will not see a velocity, a VT graph. You're not going to see a line on a VT graph that has curves and curves to it, because in this course we only look at constant acceleration. We do not look at changing acceleration. So the lines on a VT graph will either be horizontal or they'll be straight, heading down to the right, or perhaps heading up, down to the right or heading up to the right. Let's take a look at our first practice problem. So this is a qualitative practice problem. And an arrow is launched vertically upwards, moves straight up to a maximum height, then falls back down to the ground. Here's its trajectory. And the question asks, which choice below best represents the arrow's acceleration at different points? So A, B, C, D, and E. So it's a ranking task. So pause the video for a moment and take a shot at this to see if you can figure out what's going on and Which is the correct answer? So here's our answer. A equals B equals C equals D equals E. They're all equal. So what sometimes happens is students will see this and imagine, okay, well, I've thrown a ball up in the air and I throw it up, and as soon as it leaves my hands, it's going really fast, and all of a sudden I see it slowing down, and then it gets to the top of its trajectory, and for a moment, it's almost like it's zero for a moment, then it starts falling back down. It's going faster and faster. So students make the mistake of looking at this situation and they're thinking about velocity, because if that was the case, if we were asking about velocity, you would have been right. A would have been greater than B than C. So, but it's not. It asks about acceleration. And once that arrow is shot and it's in the air, the only acceleration is negative 9.8 meters per second squared. And that's our acceleration due to the force of gravity. Let's take another look at this one. Arrow is launched vertically upward, moves straight up to a maximum height, then falls to the ground. The trajectory of the arrow is noted. Which graph best represents the vertical velocity of the arrow as a function of time? So we're still ignoring air resistance. So the arrow is shot, it's in the air, the only force acting is gravity. And let's take a look. Well, you take a moment and look at these and see if you can figure out which one is the answer. But I'll give you some clues. Remember that this is the origin of the VT graph, 0. So anything above here is considered positive velocity. So that'll help you when you look at the direction of the arrow. If it's positive heading up, it should be up here. And then if it's negative velocity, the arrow is heading down, it should be down here. So now you'll just have to look at the magnitude to see, is it speeding up as it heads up or is it slowing down? All right, I'll give you a moment. Go ahead and hit pause and see if you can determine the correct answer. All right, so here's our answer. And as you can imagine, if the velocity right here is 0, and we take this out here halfway, you think to yourself, oh yeah, that makes sense, because this, when it reaches its peak, is 0. And that would be halfway through the flight of the arrow. This is half time, and this is the other half of the time. So it takes half the time to go up, takes the other half to come down. So the velocity is 0 at the maximum height. So something else is, in this course, you're never going to see curves on the velocity graph here. And then over here, this one. So C and D are out. And the reason is because it's curved on the VT graph, it lets you know acceleration is changing. And we don't study changing acceleration in AP physics. We're only looking at constant acceleration. So anytime you see a VT graph that has curves on it, you rule those out immediately and you start focusing on the other graphs. This is a great question too, because students kind of fall into a trap of looking at the masses of the arrows and then getting tricked. But you're not going to get tricked on this one. So here we go. So the figure below shows 5 arrows with differing masses. They're launched straight up with the noted speeds listed up here up top. Rank the arrows from greatest to least on the basis of the maximum height the arrows reach. We're going to ignore air resistance, and the only force acting on these arrows is gravity. So they've been launched, they're out of the bow, they're out of the off the launching pad. So anyways, they're just regular arrows, and they're heading up. So the mass doesn't matter. It's only the speed of the arrow that is taken into consideration. So if you launched a bowling ball straight up, and after you launched it, and we record the speed, and it was 6 meters per second, we do that, we go, okay, oh, look at that bowling ball go. And let's say we did the same thing with a golf ball. We got a golf ball, and we launched it at 6 meters per second. And oh, look at that golf ball go. Well, if we launched the bowling ball and the golf ball at the very same time, and they were released from the slingshot or the launching apparatus, whatever it was, at the very same time, and at the moment it left that launching apparatus, if they were both traveling at 6 meters per second straight up, they are going to they're going to hit the same height. They are going to go to the same maximum height. And a lot of times students are like, how can that be? How can that be? Well, the fact is the biggest difference is in the launching apparatus. The launching apparatus, you'd have to think to yourself, if I have to launch a bowling ball at 6 meters per second and I have to launch a golf ball at 6 meters per second, which launching apparatus has to exert more force to get that mass to 6 meters per second? And you're smart. You're like, it's the golf. It's got to be the bowling ball, not the golf ball. It's got to be the bowling ball. And you're right. The interesting thing is that's not what they're asking you here in this question, and that's why you have to be very careful with these questions here, because kids will start looking at the masses and then get trapped into that number. And since we haven't talked about forces, that's another reason why it may be a challenge when you look at it, and that's why I'm giving you a tip right now on this one. So with this problem, you only want to be looking at the velocities only. So go ahead and take a moment and answer the question, hit pause, and whenever you're ready, hit play. And there's your answer. And it's based on the velocities. Biggest, next biggest, here, and then this one B, and then last but not least E.